In this video we are going to explain a very strange and a peculiar problem named the kidnapped. Yes, the kidnapped robot problem. Now please stay with me. This is rather an advanced topic within the particle filter, but nonetheless it is very important, and if you implement the algorithm that I'm about to explain, you will have a much more accurate and robust algorithm. So let's start. Let's say that our robot is over here, and hopefully if you have done everything correctly, after several iterations and resamplings, all the particles will converge to the true position of the robot. Now, if I add some noise, they will converge to the vicinity of the true position of the robot. And this is great, and this is what we have been talking about in this section. But what happens if some evil person comes and kidnaps the robot? Now, I know it sounds very strange, but please stay with me. So, the kidnapper takes the robot from here and moves it over here. Now, what would happen? All the particles now are inconsistent with the true sense function. Why? Because let's assume that I have a landmark over here. This will be L1 and a landmark over here, L2. Now the robot senses those landmarks like here and like here. But all the particles sense something completely different. This particle, for example, senses L1 from here and L2 from here. And this is very, very different. Now, we will have no particle that will match the true position of the robot. Now, you might say, yes, but this particle on the left side will have higher probability than this particle on the right side. And you are absolutely correct. And if you will do it long enough, what you will see is that many particles will go to the left side of the cluster. However, most of the time in real-world situations, the algorithm will not be able to recover from this kidnapping scenario. Now, people again usually don't go and kidnap robot, but why is it so important? Why this scenario is so useful in real-time applications? And the answer is very simple. Sometimes the number of particles is relatively small. Sometimes, due to bad luck, most of the particles will converge to a different position than the actual robot's position. And when it does happen, there is almost nothing we can do to make the algorithm recover. So what do? There are two options. Option one, increase the number of particles. If you spread many more particles within the region of interest, it solves all of your problems. But adding particles has its own flaws. But there is another option, very efficient and very easy to program. After the resampling phase ends, when you resample all the particles according to the likelihood and weight, you take approximately between 5 and 10% of the particles and respread them evenly within the region of interest. So for example, let's move our robot to here again, and when we finish resampling, we add approximately 5 to 10% of the particles evenly in the region of interest. Over here, over here, over here, over here, and over here. Now, what will happen? If nothing bad happened, if no one kidnapped the robot, what will happen is that those particles will die in the next phase. Why? Because their likelihood is extremely small compared to the likelihood of a true particle or a particle in the vicinity of the true position of the robot. But if someone does kidnap the robot, then this particle here will have much higher weight or likelihood than all the other particles over here. In the next phase, we will see many more particles in the vicinity of the true good particle. And this is a very efficient way to handle the kidnap robot scenario. Again, what do? After the resampling phase, you take approximately between 5 and 10% of the particles and we spread them evenly in the region of interest. That's all. This tiny change can make your algorithm much more accurate and much more robust.